Thank you for the introduction. So, as you see from the picture in the front here, I'm from Norway. So when it comes to CCS in Norway, we're talking offshore storage. And many of you probably know about the projects Snøhvit and Sleipner in Norway. These are relatively famous offshore CCS projects. And SINTEF, which is the company I come from, we have been working side by side Statoil to enable these projects. And in Norway, the goal now is to scale up and ensure that we can have large-scale CO2 storage. And the hope is that the Norwegian continental shelf can, in fact, be a storage place for the whole Europe. So I'm going to talk about some of the work that has been done in the big CCS research center at SINTEF, where we have been studying various ways that leaks can develop in wells. And this topic is important. In the IPCC, they actually identified active and abandoned wells as the main or the most probable leakage path for CO2 from the storage reservoir. And what you see here is a casing, cement, and rock foundation. And when you're going to cement a well, then it's always very difficult to ensure that you have a centralized casing all the way throughout the well. So it's kilometers down to the reservoir. And in this case, that's very important because the flow of cement will be altered by the casing centralization. And then after cementing, you can, of course, have a variety of flow paths. You can have leakage between the casing and the cement, between the cement and the rock, or through the cement, either through the porosity of the cement, or through cracks in cement, or through degraded casing. And this is, of course, the same. When you plug the well, you will again be struggling with leakage paths at the edge of the plug or through the plugging material. So what we did in the big CCS project, it was that we wanted to try to find out what the size of the apertures of these leakages are. So how large are these microanalysis that people are talking about, and why and where do they most likely occur in a well? So what we did was to first make some small samples, as you see here, with a hollow rock cylinder with cement inside. And then we varied the surface properties of the rock, so they were either mud-covered or clean. And we used two muds that are very typically employed, so oil-based mud or water-based mud, both commercial muds that are used by industry. And then we scanned these samples using microcomputed tomography, and then reconstructed them in 3D. And we identified the porosity at the interface between cement and rock. That's the pinkish stuff that you see in the volumes here. And we did that for a lot of samples. I'll show you 6 of them here. So we also had filter cake at the edge of the sandstone and the cement. In this case, you see the no mud, the water-based mud, and the oil-based mud cases. And this is relatively interesting because in Norway, the oil-based mud is, the use of the oil-based mud is restricted because they're afraid of leakage of the hydraulics when you're drilling the well. But what you see here is that the oil-based mud is actually giving the best bonding compared to the water-based mud, both for a sandstone and a shale sample. And the V here is the volume of the flow paths, while the B is the bonding percentage. So it's the surface, the percentage of the cement surface that is in direct contact with rock. So if it's 100%, then you have perfect bonding. And then the more interface pores you have, the lower the bonding percentage. And then this no mud situation, where you don't have anything at the interface, that's of course a simplification that you cannot achieve in a well. Usually if you use spacers, etc., then you will still have some mud at the interface when you do your cementing. So, and then we did a lot of mapping of this for the rock cement surface. And we did the same also for casing cement. So then we made a variety of samples, again mapping using micro-CT, the interface pores. And in the case of cement, we saw very few pores at the interface. So the casing is gray here, and when it looks bluish, it's because it's surrounded by a layer of mud-affected cement. But the porosity in this case was all at the interface. So of course, to be able to determine any type of leakage from these samples, you would have to check the properties of this mud-affected cement in each case, because there was very little porosity that could be seen by CT. And what was interesting is that this very good bonding that we saw in this case seemed to be a geometry effect, because at we were making these samples in autoclaves, and at the outer surface of the autoclave, you saw more debonding. So this is exactly the geometry that was used when we looked at the cement rock bond. Then you had a rock surrounding a cement. So that might be something related to geometry there, and that's something we're looking into right now. And then when we have all these leakage paths that are mapped by micro-CT, then we can use these directly in for simulations. So we can actually import the micro-CT volume into Abacus to do flow simulations. So this is where you had a lot of leakage paths. You can see that with the green here, that's a high flow velocity. And this is single phase flow, just steady state flow that we simulated here. But we see that in the case of a very well-bonded rock, then you also have areas where you have very, very little leakage. So what we found is that even very small, well-bonded areas of cement can be a very efficient barrier towards leakage. While when you have a lot of interface porosity, then of course this has a very high porosity. What we measured when we compared the simulations with actual measurements of flow through this course was that the interface region had a very high permeability, between 1 and 10 Darcy. So that's a really high porosity, similar to sandstones that we use to inject CO2 into. And then in addition to all these defects that I've gone through now that can be present at well constructions that are decided by which materials you use and which procedures you use for well construction, you can also have this operation-induced damage to the well. So in this case, we looked at the temperature variations in the well, because when CO2 is expanding, you have a cooling due to the Joule-Thomson effect, and that can be the case when you're injecting into a very depleted reservoir, or if you have a leak in the well. And then, of course, the casing will expand and contract more if this is repeated several times, so it cycles, than the surrounding cement and rock. And this can be very damaging to the well. You can have these tensile radial stresses or tensile hoop stresses that can cause debonding or radial cracking in the well. So to look into this, we first did some very simplified simulations using Abacus, where we just exposed a very idealized, centralized sample to temperature variations between 10 and 90 degrees. And what we found was that in this idealized case, we have a very low stresses that are building up in the sample, all less than 1 megapascal. But what we were wondering was whether this is actually representative for what is going on in real life. So we wanted to get some experimental-based information on this case. And we decided to do that by using an existing setup that we have at SINTEF to study how temperature variations actually affect the well. And we have a setup where temperature variations can be, where samples, as you see here, with rock, cement, and casing, can be exposed to radial temperature variations. So this green slab that you see here is just isolation, and the temperature variations in this case are purely radial. So this copper rod is both heated and cooled at a very controlled rate, so you can put temperature cycles at will between -50 and 200 degrees on this temperature platform. And then what we're actually measuring is that we're scanning these samples in a medical CT, and again looking at how defects in the cement, for example the cement rock debonding, voids in cement, or casing cement debonding, is evolving with time. So here you see a typical sample before any thermal cycling, showing that it's very difficult to get a really good cement job, even in the laboratory. It looks a little bit worse than it is. The blue here is debonding between casing and cement, and the green is between rock and cement. And this is even before any cycling. So just to show you that this has been tested for the temperature range that we looked at, so 10 to 90 degrees, we have tested this, this setup. Here you see what is going on after 3 cycles. This is before cycling and after 3 cycles. And you see the volumes of each of the defect types that we've gone through here. And for the perfectly centralized casing, you see that very little is happening during cycling, at least for only these 3 cycles that we have tested so far. While for the off-centered casing, you can actually see that a crack is developing in the sample. So this crack was on the thin side of the cement. So here you have a 50% casing offset. And then you can, of course, plot how this debonding is varying with each cycle. Here you see the 3 first cycles where little is going on in the centralized sample, and where you see quite a lot going on in the off-centered sample. And then what we are doing is to use these samples to actually again, put them into Abacus. So map the defects, the digital defects from CT onto Abacus mesh, and then expose the sample to temperature variations, same temperature variations that we have in the laboratory. And then we get a completely different picture of the stresses building up in the sample. So here we saw that with the defects in the cement shed, you can actually get quite strong stresses in the sample. And this is now ongoing work where we are trying to predict what is going on, and in addition test it in the laboratory. And we are measuring parameters that can be used as input here, for example, the bonding strength, etc. So I made a little summary here that it's very difficult to get good bonding, and when you have some leakage paths that have appeared in your sample, then these can actually have relatively high permeabilities. So I just made the electrical analog here, where flow is actually going through the smallest resistance. And that's also the case if you have a connected leakage path in a well. And also the importance of defects. If you want to do any kind of simulation here, you see that the idealized case, where everything is centralized and there are no defects in the cement, gives a very different picture to the one where you actually have some defects in the cement. So, thank you for your attention.
We have some time for some questions for Malin.
Please speak up, because I hear very bad.
Yeah. I was just wondering how many, what fraction of the existing wells are perfect?
I think that's very, very low fraction. So what we I know that in Gulf of Mexico they had a test of 15,500 wells, where they checked the occurrence of this sustained casing pressure, which means that that pressure is actually building up outside your casing, and even if you bleed it off at the surface, then it just continues to build up, and this is of course an indication that you don't have perfect zonal isolation in the well, and there they found that it was when the well is 15 years old, it has a 50% probability to have trouble with leakage. And I think among the 1.8 million wells in the world today, I think they estimate that about 30 to 35% have problems with this sustained casing pressure. So I think the defects are really important to take into account in this case.
So what do you do about it?
Yeah, that's actually one of the things that we want to look at in the big CCS project. So we are going to look at different ways of remediating these faulted wells. So now that we are creating these problems in the laboratory, then we can also check how they can best be remediated. Because in order to plug a leaking annulus, you would at least need to know what kind of apertures you're trying to plug, what kind of viscosities of remediation fluids are needed, etc. So that's one of the goals, one of the things that we want to look into.
Can you give a ballpark
Yes, we have some. You can look into the papers. It varies a lot. So in the case where you have a filter cake, for example, so it means that the mud has been filtrated through the rock, then we see very, very large apertures compared to in the case where we have no mud, for example. So this shows that if you have, or if the ones that have been drilling the wells have actually used spacers and presflushes and done good work when it comes to mud removal before the cementing, then they probably have less problems with this kind of debonding issues compared to in wells where little effort has been made.
Okay, one more quick question and then we'll move on.
In all the experience with CO2 EOR, have the fluxes of these kinds of fluxes through the wellbore been quantified for those applications?
I'm not aware of any issues where they have actually looked at the fluxes through EOR wells, but there's one study that I'm aware of, at least from the Sackrock field, where they have actually taken some cores out from a well that has been used for CO2 injection. And what they found there is that the interface that seems to have had most CO2 leakage is the one between the cement and the rock, which is in agreement with what we see here, that we have more trouble with getting good bonding, especially due to the geometry. If you have shrinkage, cement might shrink inwards, and the cement rock interface is maybe the one that is most critical